Hey everyone. So in today's lesson, we're going to be talking about exoplanets. Now this is something that we may have talked about sort of in passing a couple of times in class, but we're going to talk in a little bit more detail about them today. And we're going to talk about what they are, why they're important, and what it'll mean if we find certain types of exoplanets. All right, so we'll talk about different types of them. We'll talk about what they are, how to find them, things like that. All right, so basically, an exoplanet is a planet that's orbiting another star, basically. All right, so it's a planet in another solar system. So exoplanets, let me make this a exoplanets are planets orbiting stars other than our sun. Okay, so exoplanets are planets that are orbiting stars other than our sun. So basically, the definition of a planet when the International Astronomical Union defined what a planet is, there are three requirements were that the planet must be round, it must be big enough to become a sphere under its own gravity, which is fine. It must clear out its neighborhood of debris, which is the reason that Pluto's not a planet, is because it failed that criterion. But the third thing was they came up with this decision so quickly that their third statement for what must be true in order for something to be considered a planet is that it must orbit the sun. So they didn't say that it must orbit a star, they said that it must orbit the sun. So exoplanets, I guess you could say that they're not regular major planets like in our solar system because they don't orbit the sun. So they're called exoplanets instead to differentiate them from the planets of our solar system. You may also see the name extrasolar planets. Extrasolar planets. That's just another name for exoplanets. All right, so basically they are any type of planet, anything that you would normally consider a planet. So not something like the moon or an asteroid would not be considered an exoplanet, but if you had something that was about the size of Earth and it orbited its parent star and not a bigger body, then you could, if it was in our solar system, you would consider it a planet. So in its solar system, we call it an exoplanet because it's not in the same solar system as us. All right, so for example, if you had aliens in the next star system over and they looked at our solar system, they might consider, Pluto to be a planet or whatever, so we'll leave Pluto out of the equation. But for example, asteroids in the asteroid belt or comets, those would not be considered exoplanets. Those would just be considered, asteroids. But the Earth would be considered an exoplanet if they could see it. Things like Jupiter and Saturn, they would be considered exoplanets for sure. Those would be the two biggest, the two most likely objects to see because they're the two biggest. So Jupiter, Saturn, all the rest of the planets would be considered exoplanets to aliens in another solar system, but the moon, asteroids, comets, things like that would not be considered exoplanets. So it needs to be something that we would call a planet. All right, now, why are they important? So they're important because, if you look at our solar system, there are certain regions where you might expect to find living things, and then there are regions where you wouldn't expect to find living things. All right, so let's think about life that we have on Earth. If Earth was, several hundred degrees, like let's say if the surface temperature on Earth was 500 degrees Celsius, chances are you might if you're lucky, get some form of microbial life, but you wouldn't see the diversity of life that we see today. We're not suited for this type of temperature range. This is about the temperature range that you would find on Mercury during the day. But similarly, just in the other direction, if Earth's average surface temperature was something like this, negative 175 degrees, then again, you might be lucky to get a little bit of microbial life, by chance, but you're not going to see the diversity that we see on the Earth today. And the reason for that is that every single creature that we know of needs liquid water. All right? Everything on the surface of the Earth, in order to survive, needs water. At 175 degrees below zero, that's going to be in the form of ice, which is not quite as useful. And if it was 500 degrees, then we would have a bunch of steam everywhere. So again, not useful. You need a specific region between 0 and 100 degrees Celsius, because that's where you'll find liquid water. So if you're on a planet where the average daily temperature is 500 degrees Celsius, you're not going to find any liquid water there. You're not going to find any life there. If the average daily temperature is minus 175, once again, you're not going to find any liquid water. So at least as far as we know, you're probably not going to find any life there either. Now, there are some exceptions, not to this water rule, but to the idea of where you might find liquid water. So if you look at our solar system, let's say we got the sun here, and then we got Mercury, Venus, Earth, Mars, Jupiter, Saturn with its rings, Uranus, and Neptune. All right, very rough drawing of the universe, not of the universe, of the solar system. So if you look over here, we've got Mercury and Venus, which are both extremely, extremely hot. So here, no liquid water, no life, right? Earth, we've got liquid water, great. Mars onwards, no liquid water, no life. All right, so basically that's telling us that somewhere in this region, in between Venus and Mars, there's this magical region where you get liquid water. Any closer, so here you get liquid water, any closer to the sun, and you get steam, which is not useful, as we've talked, and further than that, you get ice, which is also not useful, right? You want that magical region in the middle, which has liquid water. And this region is called the habitable zone. You don't have to make the entire drawing, but you should know that the habitable zone is the region in space where liquid water can exist on the surface of a planet. All right, so I'll write that down. So the habitable zone is the region in space where liquid water can exist on the surface of a planet. Okay, and this bit about the surface is important. I'm sorry that's a little bit small and you can't read it, but the bit about the surface is important because we know there's liquid water on Earth, we know there's ice on Mars, and we know that Venus and Mercury are way too hot, at least during the day, for liquid water to exist on their surfaces. But Jupiter has a moon called Europa, and Saturn has a moon called Enceladus, and both of them show strong evidence of having liquid water underneath the surface. So that's where this bit about the surface comes into play for the definition of the habitable zone, because they're very clearly far, far away from the sun, and their surfaces are covered in ice. They are outside the habitable zone, but basically what you have on those moons is you have basically, so you've got the surface of the moon, which is covered in ice, but then inside that they've got some core of rock or metal or whatever, but then in between the ice shell on the outside and the core, they've got a liquid water ocean. And basically that water is protected from the freezing cold space, because it's so far away from the sun, by this shell of ice on the outside. And it's possible, since there's liquid water, it's possible that there's microbial life there. Now, nobody's found any microbial life there yet, but it's a possibility. For life as we know it, this is the type of thing we'd be looking for, something that has liquid water on it. Now, if you're looking into another solar system, looking at a moon and trying to figure out if it's got water underneath the surface is really difficult. So when it comes to exoplanets, that's not really what we're interested in. What we're interested in is planets like Earth, that if you look at the exoplanet system, if you look at the extrasolar system, the other solar system, and you've got this habitable zone, which you can actually calculate where it should be based on the type of the star. If you can see any planets or detect any planets in that habitable zone, then there's a chance that it has liquid water, and there's a chance that it has life. So that's what scientists are looking for when they're peering deep into space looking for planets, is they're looking for planets in this magical ring at some distance away from the star. All right, so basically I'm going to leave that there. For any star, for different types of stars, the distance will be different. But basically, for every star, there's this region of space where if there's water on the surface, it'll be in liquid form. Any closer and it'll be steamed, where it's too hot, and any further away and it'll be ice or too cold. All right, so when you're looking for exoplanets, if you find an exoplanet that's sitting right here, that's not really helping you in your quest to find life. But if you find an exoplanet that's here, it'll be worth doing some digging to see if you can figure out the composition of that planet. Same thing if it's out here, and you'd be really lucky if you get one that's smack dab in the middle. And if you can do some work to try and figure out the composition of that planet, and you find that there could be water on that planet, then chances are somewhere on the surface of that planet it's in liquid form. So this is what astronomers are looking for when they're looking for these types of planets. Now, the other problem with these exoplanets is that they can be really, really hard to detect, and we're going to talk in the next part of this video about a couple of ways that astronomers use to try and figure out if a star has planets orbiting it. Now, there are a few different types of exoplanets. You have the ones that we want are Earth-sized exoplanets in the habitable zone, but you can find exoplanets that are a lot bigger, and it's kind of a consequence of the techniques that are used to detect these exoplanets. There's a main type of exoplanet, or the first type of exoplanet that was discovered, is called a hot Jupiter. So we got types of exoplanets. Let me write this down. Types of exoplanets. So there are several types of exoplanets. We're just going to talk about a couple of them really quickly. One of them is hot Jupiters, and basically that's pretty much what it sounds like. It's a Jupiter-sized exoplanet. A Jupiter-sized exoplanet. orbiting very close to its parent star. And when I say very close, I mean very close. So Mercury, the closest planet to the Sun in our solar system, takes 88 days to orbit the Sun once. Hot Jupiters have been found that orbit their parent star in about 4 days. So that's way, way, way closer to their parent stars than Mercury. A second type of exoplanet, just really quickly, is called a super-Earth. And these, we'll only talk about these two. They're called super-Earths. And basically they're planets that are sort of, they're in the habitable zone or they are very close to the habitable zone, in or near not all super-Earths will necessarily fit this criterion, but this is for the ones that we're interested in. They should be in or near the habitable zone. But the key thing with them is based on their size. So both of these are based kind of on size, but also kind of on position. So for example, a hot Jupiter has to be relatively close to its parent star, otherwise it's not going to be very hot. But a super-Earth is, roughly, 2 times the size of Earth. So it's, a couple or a few times bigger, a few times larger than Earth. But if you remember, Jupiter is about 10 times bigger than Earth and has a much, much stronger gravitational pull. So even if we found one in the habitable zone, it would be difficult for creatures like us to actually live there. But with super-Earths, they might still be bigger and have a slightly stronger gravitational pull, but they might be sort of survivable. Now, there are Earth-sized exoplanets as well, which are tremendously difficult to find just because they're so small. So I'm actually going to stop there for this video. We'll pick up in part 2 talking about how to find exoplanets and why it's so easy to find big ones instead of small ones.